For centuries, humanity perceived the cosmos as a static, unchanging backdrop, a grand stage upon which terrestrial events unfolded. Ancient civilizations charted the predictable movements of stars and planets, believing them to be fixed points of light in an eternal, immutable firmament. Yet modern cosmology reveals a truth far more profound and dynamic. The universe is not a finished masterpiece, but an endlessly evolving canvas, ceaselessly forming, transforming, and renewing itself in ways both subtle and spectacular. Every second, somewhere in the vastness, new cosmic structures are taking shape, changing the very fabric of existence. This ongoing cosmic creation is not limited to isolated events. It's a fundamental principle woven into the very fabric of space and time. From the smallest particles coalescing to form nascent stars, to gargantuan galaxies merging in gravitational ballets, the universe is a perpetual workshop. It's a place where elemental forces are constantly at play, shaping and reshaping matter and energy into new configurations. This dynamic evolution means that the cosmos we observe today is markedly different from how it appeared billions of years ago, and will continue to evolve into something entirely new in the eons to come. To understand this ongoing formation, we must first briefly peer back to the very beginning, to the fiery crucible, just moments after the Big Bang. This profound event was not an explosion into existing space, but rather the astonishing expansion of space itself from an infinitely dense, hot point. In these earliest fractions of a second, the fundamental forces of nature emerged, shaping the universe's initial conditions. This rapid expansion, known as inflation, smoothed out irregularities and set the stage for the formation of everything we know today, from the smallest atom to the largest galaxy cluster, a complex dance of cosmic evolution. In the immediate aftermath of the Big Bang, the universe was an incredibly hot, dense plasma, a chaotic soup of fundamental particles like quarks and electrons, far too energetic for atoms to form. Light particles could not travel freely, constantly scattering off the charged matter. This era, lasting hundreds of thousands of years, was a period of intense activity, yet it laid the groundwork for all subsequent cosmic evolution. Imagine a universe so opaque, so brilliantly luminous, that it completely obscured any emergent structure. It was an environment of raw, undifferentiated energy, barely cooling from its initial, astonishing temperature. Approximately 380,000 years after the Big Bang, a pivotal transformation occurred as the universe continued to expand and cool. Electrons finally combined with atomic nuclei, primarily hydrogen and helium, in an event called recombination. This process rendered the universe transparent, allowing photons, particles of light, to travel freely for the first time. The light released during this era, stretched and cooled by the universe's expansion, is what we now detect as the cosmic microwave background radiation, a faint but pervasive glow that acts as a snapshot of the young cosmos, a relic of its earliest moments. Following the transparency of the universe, a period known as the Dark Ages ensued. This was an era lasting for hundreds of millions of years, not because there was no light, but because there were no new sources of light, no stars, no galaxies. The universe was filled primarily with neutral hydrogen and helium gas, softly glowing from the lingering warmth of the cosmic microwave background. This seemingly uneventful period was crucial, however, as tiny density fluctuations, the seeds of future cosmic structures, began to slowly grow under the relentless pull of gravity, accumulating matter that would eventually ignite the first stars. Driven by gravity, the slightly denser regions of matter that formed during the Dark Ages began to draw in more and more surrounding gas. Over tens of millions of years, these nascent clumps grew steadily, eventually becoming massive enough to collapse under their own tremendous weight. At the hearts of these collapsing gas clouds, temperatures and pressures soared to unimaginable levels. This was the birth cry of the universe's first generation of stars, known as Population 3 stars, marking the dawn of the cosmic light and the end of the long Dark Ages. Their appearance dramatically reshaped the early cosmos. These first stars were colossal, far more massive than our Sun, and composed almost entirely of hydrogen and helium from the Big Bang. Without heavier elements, their life cycles were incredibly short, but spectacularly violent. They burned through their fuel rapidly, shining with an extraordinary brilliance. Their intense ultraviolet radiation eventually ionized the surrounding neutral hydrogen gas, fundamentally changing the cosmic environment in a process called reionization. This transformed the universe from opaque to transparent on a grand scale, illuminating the nascent cosmic web and paving the way for the emergence of complex structures we observe today. As these titanic first stars reached the end of their brief but spectacular lives, they met their demise in truly cataclysmic fashion, through supernovae explosions of unprecedented power. These superluminous events seeded the early universe with the very first heavy elements: carbon, oxygen, iron, and many others, forged in their core during nuclear fusion and scattered outward during their violent deaths. Without these explosions, there would be no cosmic dust, no rocky planets, no complex chemistry, and ultimately, no life. The brutal end of the first stars was, in fact, the essential beginning for all that followed. The remnants of these primordial supernovae, enriched with newly forged heavy elements, became the building blocks for subsequent generations of stars and, crucially, for planets. These newly synthesized elements mixed with the pristine hydrogen and helium, forming molecular clouds that were denser and richer in potential. Over billions of years, this cosmic recycling process continuously enriches the interstellar medium, providing the raw materials for more diverse stellar populations. Each new generation of stars contains a slightly higher proportion of heavier elements, demonstrating the universe's gradual evolution from a simple to a complex chemical composition. Our own Sun, a second or third generation star, is a direct beneficiary of this cosmic history. It formed from a molecular cloud that had been enriched by the supernovae of countless stars before it. This enrichment was crucial, as the presence of heavier elements like carbon, oxygen, and silicon was absolutely essential for the formation of rocky planets like Earth. Without these elements, no solid cores could have condensed, no atmospheres could have formed, and the diverse chemistry necessary for life would simply not exist. Our existence is intrinsically linked to the violent deaths of stars that lived and died long before our solar system came into being. Today, the process of star formation continues unabated within the vast, cold, and dense regions of giant molecular clouds. These interstellar behemoths, spanning hundreds of light years, are the universe's stellar nurseries. They are primarily composed of hydrogen gas and interspersed with dust particles, all at extremely low temperatures. Within these clouds, often triggered by shockwaves from supernovae or galactic collisions, pockets of gas begin to collapse under their own gravity. This gravitational collapse is the very first step in the birth of a new star, a process that can take millions of years to unfold, shaping the future of galaxies. As a region within a molecular cloud collapses, the increasing density and pressure cause it to heat up, forming a dense core known as a protostar. This nascent star isn't yet fusing hydrogen, but it radiates energy from the gravitational collapse itself. Protostars are deeply embedded within their natal clouds, hidden from immediate view, often surrounded by dusty cocoons. They continue to accrete more material from the surrounding gas and dust, growing in mass and temperature. This infall of material creates powerful outflows, known as bipolar jets, blasting away remaining gas and shaping the surrounding nebula, a dramatic and chaotic process. Millions of years later, as the protostar continues to contract and heat, the core eventually reaches the critical temperature and pressure, approximately 10 million degrees Celsius, required for nuclear fusion to ignite. At this point, hydrogen atoms begin to fuse into helium, releasing enormous amounts of energy. This outward pressure from fusion precisely balances the inward pull of gravity, and the star achieves hydrostatic equilibrium. A main sequence star, like our Sun, is born. This stable phase can last for billions of years, providing a steady source of light and heat, fueling planetary systems, and fostering the potential for life. Stellar evolution is a continuous cycle of birth, life, and death, driven by gravity and nuclear processes. Stars come in a vast array of sizes and colors, from the diminutive red dwarfs that can live for trillions of years, quietly burning their fuel, to the colossal blue giants that blaze brightly for mere millions before spectacular demise. Each stellar type represents a different path through the universe's ongoing formation. Even as new stars ignite in one part of a galaxy, others are aging, expanding into red giants, or collapsing into white dwarfs, neutron stars, or black holes, constantly adding to the cosmic architecture. The leftovers from stellar formation are not wasted. As a protostar forms and accretes matter, the surrounding material flattens into a vast, rotating disk known as a protoplanetary disk. This disk is composed of gas and dust that didn't fall directly onto the central star. Within this swirling, dusty environment, the next crucial stage of cosmic formation unfolds: the birth of planets. These disks are incredibly common around young stars throughout our galaxy, indicating that planet formation is not an anomalous event but a widespread, ongoing process, continually populating the cosmos with new worlds. Within the protoplanetary disk, dust grains, initially microscopic and no larger than soot, begin to collide and stick together. This sticky process, driven by electrostatic forces and gentle collisions, gradually builds larger and larger aggregates. It's a bit like dust bunnies forming in a cosmic attic, gradually accumulating mass. As these clumps grow, they attract more material, leading to a runaway growth. This is the first crucial step in constructing planets from the ground up, a delicate chemical dance happening billions of times across the galaxy, constructing the solid foundations of future worlds. As the dust grains clump together, they eventually form objects a few kilometers in size, known as planetesimals. These larger bodies are massive enough for their own gravity to start playing a significant role. Planetesimals begin to gravitationally attract one another, leading to more energetic collisions and a more efficient growth process. Some collisions shatter the growing bodies, while others lead to mergers. This chaotic but ultimately constructive phase continues for tens of millions of years, clearing out the protoplanetary disk as most of its solid material is incorporated into larger and larger structures. Through this relentless process of accretion, planetesimals gradually grow into full-fledged planets. The more massive a body becomes, the stronger its gravitational pull, enabling it to sweep up more material from the surrounding disk. For rocky planets like Earth, this process typically involves the accumulation of solid material. For gas giants like Jupiter, once a rocky core reaches a certain critical mass, it can rapidly accrete enormous quantities of hydrogen and helium gas from the outer, cooler regions of the disk before the stellar wind blows the gas away. This dual pathway explains the diversity of worlds in our solar system. The discovery of thousands of exoplanets in recent decades has dramatically expanded our understanding of planetary formation. We now know that planetary systems are incredibly diverse, often differing wildly from our own solar system's architecture. Some stars host hot Jupiters, orbiting incredibly close, while others have systems with multiple super-Earths. This ongoing discovery pipeline is not only finding new worlds, but also refining our models of how planets form, suggesting multiple pathways and outcomes. Each new exoplanet detection is a testament to the universe's persistent ability to create new worlds, constantly expanding the cosmic real estate. While stars and planets capture our immediate attention, the grandest structures in the universe are galaxies. Colossal collections of billions of stars, gas, dust, and dark matter, all bound together by gravity. Galaxy formation is also an ongoing process, spanning billions of years and continuing even today. Early in the universe's history, smaller clumps of matter, often called proto-galaxies, began to merge and accrete more gas. These early building blocks slowly assembled into the much larger and more complex galaxies we observe in the modern universe. Galaxies are categorized by their shapes: spiral, elliptical, and irregular. Spiral galaxies, such as our own Milky Way, are characterized by their rotating disks of stars, gas, and dust, with prominent spiral arms where new stars are actively forming. Elliptical galaxies are more amorphous, often older, and contain less gas and dust, with star formation having largely ceased. Irregular galaxies, as their name suggests, lack a defined shape, often resulting from gravitational interactions or collisions. The specific shape a galaxy takes is a result of its formation history, including the number and types of mergers it has undergone. One of the most dramatic forms of galaxy formation and evolution is galactic mergers. When two galaxies, drawn together by their mutual gravitational pull, collide, it's not typically a head-on smash of individual stars. Stars are so widely spaced that direct stellar collisions are exceedingly rare. Instead, the gravitational forces tear apart and reshape both galaxies. Gas and dust clouds within them are compressed, triggering intense bursts of star formation, leading to a flurry of new stellar births. This cosmic dance ultimately results in the formation of a single, much larger galaxy, usually an elliptical one. Our own Milky Way galaxy is currently on a collision course with its larger neighbor, the Andromeda Galaxy. In about 4.5 billion years, These two colossal spirals will begin their long, slow gravitational dance, eventually merging to form a single, enormous elliptical galaxy, often playfully dubbed Milkomeda or Milkdromeda. This future event is a prime example of ongoing galaxy formation, demonstrating that even our familiar home galaxy is not a static entity, but is dynamically evolving on cosmological timescales, constantly being reshaped by the inexorable pull of gravity. At the heart of nearly every large galaxy, including our Milky Way, lies a supermassive black hole. These enigmatic objects, millions to billions of times the mass of our Sun, are profoundly linked to galaxy formation and evolution. The growth of a supermassive black hole seems to go hand in hand with the growth of its host galaxy, suggesting a symbiotic relationship. As galaxies merge, their central supermassive black holes also merge, creating even larger ones. This process releases incredible amounts of energy, which can influence star formation across the entire galaxy. Beyond galaxies, the universe organizes itself into even larger structures. Galaxies are not randomly distributed but are arranged in a vast, intricate network known as the cosmic web. This web consists of dense clusters of galaxies, connected by long, slender filaments of gas and dark matter, which stretch across hundreds of millions of light-years. In between these filaments and clusters are enormous, relatively empty regions called cosmic voids, truly vast expanses of nothingness where galaxies are scarce. This large-scale structure is a direct result of gravity acting on primordial density fluctuations over billions of years. Galaxy clusters are among the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies, vast amounts of superheated gas, and an even greater abundance of dark matter. These clusters are constantly growing as they attract more galaxies and intergalactic gas from their surroundings. Collisions and mergers within clusters are common, leading to active periods of star formation and also stripping gas from galaxies, influencing their evolution. These clusters stand as the most massive laboratories for ongoing cosmic formation at the grandest scales, demonstrating gravity's relentless work. Dark matter plays a pivotal, albeit mysterious, role in the formation of all cosmic structures, from galaxies to the cosmic web. While invisible and undetectable by light, its gravitational influence is profound. Scientists believe dark matter forms an invisible scaffold, or a cosmic skeleton, upon which ordinary matter, the stars, gas, and dust we can see, collects and collapses. Without dark matter, matter would not have clumped together sufficiently in the early universe to form the galaxies and clusters we observe today. It is the unseen architect of the cosmos, dictating the universe's large-scale organization and ongoing evolution. The universe is not only expanding, but its expansion is accelerating, driven by a mysterious force called dark energy. This acceleration means that galaxies are moving away from each other at an ever-increasing pace. While dark energy fundamentally influences the large-scale future of the universe, within gravitationally bound structures, like galaxies and galaxy clusters, gravity still dominates. This ongoing acceleration of expansion affects how much new material can be drawn into forming structures from vast cosmic distances, potentially limiting future larger-scale formation and further isolating galactic islands in the distant future. Even after a star's dramatic demise, its remnants contribute to the universe's ongoing evolution. White dwarfs, the superdense cores of sun-like stars, slowly cool over eons, eventually becoming black dwarfs. Neutron stars, the collapsed cores of massive stars, spin rapidly and boast extreme densities, often forming pulsars. And stellar mass black holes, the ultimate gravitic remnants, absorb nearby matter, growing in size. These stellar corpses become silent beacons of past formation, but their gravitational influence and occasional interactions can trigger new events, like supernovae in binary systems, continuing the cosmic cycle. Supernovae, the explosive deaths of massive stars or white dwarfs in binary systems, are not just destructive events, they are cosmic engines of creation. They blast heavy elements forged within the star, and even heavier elements created during the explosion itself, into the interstellar medium. This enriched material then mixes with existing gas and dust. This is the crucial step that creates successive generations of stars, planets, and even life itself. Without these spectacular explosions, the universe would remain a sparse, chemically simple place, devoid of the diversity and complexity we observe today. The delicate, often beautiful structures known as planetary nebulae represent the dying breath of sun-like stars. As these stars exhaust their nuclear fuel, they shed their outer layers of gas and dust into space, creating mesmerizing shells that glow with vibrant colors as they are illuminated by the hot, exposed stellar core that remains. While not directly forming new stars, these nebulae return processed elements like carbon, oxygen, and nitrogen to the interstellar medium. These elements are then incorporated into future star-forming regions, serving as essential ingredients for the next cycle of cosmic formation. Black holes, regardless of their size, are active participants in cosmic evolution. Stellar mass black holes are the remnants of massive stars, while supermassive black holes lurk at galactic centers. Both types grow by accreting matter from their surroundings. As gas and dust fall into a black hole, they form an accretion disk, heating up to immense temperatures and emitting X-rays and other radiation. This process can be incredibly energetic, influencing the gas distribution in galaxies and thus affecting star formation rates, demonstrating an active, if extreme, form of cosmic engineering. The intergalactic medium, the vast emptiness between galaxies, is not entirely empty. It contains a tenuous plasma of hydrogen and helium, remnants of the early universe. As galaxies move through this medium, and as cosmic structures continue to form and deepen their gravitational wells, this intergalactic gas is slowly being drawn into filaments and clusters. This accretion of new gas provides an ongoing fuel source for galaxies, allowing them to continue forming new stars over immense timescales. It's a continuous, diffuse inflow of raw material that keeps the cosmic engine running. The formation of the solar system, our cosmic neighborhood, is a prime example of these ongoing processes. Our Sun, Earth, and all the other planets coalesced from a single, vast rotating cloud of gas and dust called the solar nebula approximately 4.5 billion years ago. The central part condensed to form the Sun, while the outer parts flattened into a disk where the planets accreted. This single event was a spectacular manifestation of the universe's continuous formation of stellar and planetary systems, a testament to the universality of these astrophysical principles. The Earth itself, formed through the accretion of planetesimals, continued its own intense geological formation for billions of years. Early Earth was a molten ball, gradually cooling and differentiating into layers, with volcanic activity and constant bombardment shaping its surface. The formation of our atmosphere, oceans, and continents were all parts of an immense, ongoing geological and chemical process. Even today, plate tectonics, volcanism, and erosion continue to reshape our planet's surface, demonstrating that planetary formation is not a single event, but a continuous geological evolution. The Moon, an essential companion to Earth, likely formed from a colossal impact between an early Earth and a Mars-sized protoplanet. This giant impact hypothesis suggests that the debris from this collision coalesced in orbit around Earth. This dramatic event not only formed our Moon, but also had profound implications for Earth's rotation and tilt, influencing its climate and thus the very conditions for life. The formation of planetary satellites in general is another layer of ongoing cosmic construction, adding complexity and diversity to our understanding of orbiting worlds. Even within our own solar system, subtle but continuous formation processes are at work. Micrometeorites constantly fall to Earth, adding tiny bits of extraterrestrial material. Asteroids collide in the asteroid belt, shattering into smaller pieces or sometimes forming larger aggregates. Comets, remnants from the solar system's formation, occasionally shed dust and gas as they approach the Sun, contributing to the interplanetary dust. While not as dramatic as galaxy mergers, these microscopic processes are still forms of ongoing accretion and redistribution of matter within our cosmic neighborhood. Looking further afield, the discovery of rogue planets, those unbound by a star's gravity and wandering through interstellar space, adds another dimension to planetary formation. These worlds may have been ejected from their birth systems during chaotic early stages of formation, or perhaps formed independently in dense molecular clouds without a parent star. Their existence suggests that the universe's ongoing planetary formation yields not just neatly ordered systems, but also opens up possibilities for countless solo worlds traversing the cosmic void, a testament to the diverse outcomes of gravitational dynamics. The study of exoplanetary atmospheres is revealing surprising details about the ongoing chemical evolution on other worlds. For instance, observations indicate processes like cloud formation, atmospheric escape, and even weather patterns on distant worlds. The presence of specific molecules can indicate geochemical cycles or even potential biological activity, hinting at the continuous reshaping of these alien environments. These atmospheric dynamics serve as a reminder that the formation and evolution of a planet don't cease after its initial accretion, but continue throughout its entire lifetime, a never-ending interplay of forces. Even the very elements that make up our bodies are a product of cosmic formation and recycling. The hydrogen was forged in the Big Bang. Carbon, oxygen, nitrogen, and iron, the building blocks of life, were all cooked in the fiery hearts of ancient stars and then explosively scattered across the cosmos by supernovae. Our individual existence is a direct consequence of this grand, ongoing cosmic process. We are literally stardust, meticulously assembled over billions of years from the atomic remnants of long-dead stars, making us an intrinsic part of the universe's continuous formation. The universe's persistent formation also extends to phenomena like gamma-ray bursts, the most powerful explosions in the cosmos since the Big Bang. These ultraluminous events are thought to arise from the collapse of massive stars into black holes, or the merger of two neutron stars. While seemingly catastrophic, these bursts are crucial for enriching environments with heavy elements, and can influence star formation in distant galaxies by delivering sudden, concentrated bursts of radiation. They are extreme instances of matter transformation, continually reshaping the cosmic landscape with their colossal energy. Quasars, incredibly luminous active galactic nuclei, are powered by supermassive black holes rapidly accreting vast amounts of gas and dust. These powerful cosmic engines were far more prevalent in the early universe, signifying a period of intense galaxy formation and growth for their central black holes. The energy released by quasars can be so immense that it can influence or even halt star formation in their host galaxies by blowing away gas. The study of quasars provides crucial insights into the rapid growth of structures in the young cosmos, a formative era of immense energy and dramatic change. Even galactic outflows and inflows represent dynamic, ongoing formation processes. Powerful stellar winds from massive stars and supernovae explosions can drive gas and dust out of galaxies, creating vast regions of hot, diffuse gas. Conversely, galaxies can accrete new, cool gas from the intergalactic medium, providing fresh fuel for star formation. This constant cycling of matter, both within and between galaxies, ensures that the building blocks for new stars and structures are continually redistributed and made available, highlighting the universe's efficient and continuous material transport system. The study of cosmic rays, high-energy particles originating from outside our solar system, offers another fascinating glimpse into the universe's dynamic processes. These particles, mostly protons and atomic nuclei, are accelerated to nearly the speed of light by powerful cosmic events like supernovae, active galactic nuclei, and colliding galaxies. They traverse vast distances, carrying information about the extreme environments where they are formed. Their continuous bombardment of our planet and atmosphere is a subtle but constant reminder of the intense, ongoing energy transformations occurring throughout the cosmos. The expansion of the universe itself is a form of ongoing fundamental change. Space is not merely stretching. New space is constantly being created between gravitationally unbound objects. This phenomenon means that the large-scale tapestry of the cosmos is continually being redrawn, with the distances between galaxy clusters increasing. This relentless expansion dictates the ultimate future of the universe, influencing how and where future cosmic structures might form, or, conversely, become increasingly isolated, profoundly shaping the universe's destiny. The discovery of gravitational waves ripples in spacetime caused by extreme cosmic events like black hole mergers or neutron-star collisions provides yet another window into the universe's ongoing dynamism. These waves carry direct information about the most violent processes in the cosmos, revealing how massive objects twist and accelerate space-time itself. Detecting these waves allows scientists to observe events that are otherwise invisible, providing direct evidence of colossal cosmic formation processes, confirming exotic predictions of phenomena where mass and energy reshape the very fabric of reality. The chemical enrichment of the universe is a continuous, irreversible process, directly linked to all ongoing formation. With each generation of stars, more hydrogen and helium are converted into heavier elements through nuclear fusion. When these stars die, they return these elements to the interstellar medium, enriching it further. This means that future generations of stars and planets will be increasingly metal-rich, leading to different compositions and potentially different types of worlds. This steady progression from a primordial helium and hydrogen soup to a chemically diverse universe is a cornerstone of cosmic evolution. The cosmic cycle of gas and dust is fundamental to this enrichment. Gas falls into galaxies, condenses to form stars and planets. Then, stars process the gas and eject heavier elements back into the cosmic environment through winds and supernovae. This enriched material can then seed new star formation or even be ejected from the galaxy entirely, contributing to the intergalactic medium. This continuous flow and transformation of matter over billions of years gradually changes the chemical composition of the entire universe, allowing for increasingly complex structures and chemistry to emerge. Even seemingly desolate galactic halos, the vast, diffuse regions surrounding spiral galaxies, are not static. They are continually accreting smaller galaxies and streams of stars torn from them. These interactions provide fresh gas and dark matter to the larger galaxy, fueling its continued growth and potentially triggering new waves of star formation in its disk. The halo acts as a cosmic reservoir, continuously feeding its central galaxy with new material, ensuring that galactic growth is an ongoing, dynamic process of gravitational acquisition and integration throughout countless eons. The continuous flow of gas within galaxies is orchestrated by vast stellar feedback mechanisms. When massive stars explode as supernovae, their powerful shock waves sweep through the surrounding gas, compressing it in some regions and dispersing it in others. These processes can both trigger new star formation by creating dense pockets for collapse, and sometimes prevent it by blowing gas out of the galaxy. This intricate balance of creation and disruption ensures that star formation is an intermittent, dynamic process, not a uniform constant, shaping galactic evolution. One of the most intriguing aspects of ongoing cosmic formation is the possibility of dark galaxies, hypothetical galaxies primarily composed of dark matter with very few stars or gas. If they exist, they would represent structures formed by gravity, yet failing to ignite significant star formation due to insufficient ordinary matter or other factors. Their potential discovery would be a monumental step in understanding how gravity alone shapes cosmic structures, offering insights into regions where cosmic evolution might have taken a path less luminous. The universe also experiences cosmic cold fronts, boundaries where two massive galaxy clusters collide, creating shock waves in the hot intergalactic gas that permeates them. These fronts are marked by sharp discontinuities in temperature and density, revealing the immense power of these grand-scale mergers. The gas sloshing and mixing within these events reshape the cosmic environment, demonstrating how even the most massive structures continue to interact and transform, distributing vast quantities of energy and matter across immense cosmic scales. The evolution of supervoids, the largest empty spaces in the cosmic web, is another aspect of ongoing formation. While seemingly void, these regions are not entirely empty but merely contain very few galaxies. As the universe expands and gravity continues to pull matter into filaments and clusters, these voids grow even larger and emptier over time. Their expansion and the deepening of their relative emptiness is a testament to the large-scale gravitational sorting of matter in the universe, defining the boundaries of grand-scale cosmic structure formation. The properties of black holes are continually evolving as they accrete matter. Stellar mass black holes grow as they ingest nearby gas or stellar companions. Supermassive black holes, in particular, can rapidly increase their mass during active phases when vast amounts of gas fall into their gravitational grasp. This growth process is a continuous cosmic construction project, adding to the extreme densities and gravitational prowess of these enigmatic objects, making them more influential in shaping their galactic environments and influencing future star formation. The formation of the universe's largest stars, the hypergiants and supergiants, is an ongoing process in particularly dense star-forming regions. These stars, dozens to hundreds of times more massive than the Sun, burn through their fuel at an extraordinary rate. Their immense radiation and powerful stellar winds carve out vast bubbles and cavities in molecular clouds, influencing where new stars can form. Their brief but brilliant lives are intense episodes of cosmic formation, dramatically reshaping their immediate surroundings, literally blowing bubbles in the fabric of the galaxy. Beyond the formation of individual stars, planets, and galaxies, the very nature of space-time itself remains a subject of intense theoretical study and ongoing discovery. Concepts like quantum foam at the smallest scales, or the potential for extra dimensions at larger scales, suggest that the fundamental fabric of reality may itself be dynamic and far from fully understood. While speculative, these ideas hint at an even deeper layer of formation happening at the very foundational levels of the universe, suggesting that the journey of discovery is far from over. The study of the chemical composition of stars in different parts of a galaxy reveals a history of ongoing formation. Older stars, often found in the galactic halo, are typically more metal-poor, meaning they have fewer heavy elements. Younger stars, like our Sun, found in the disk, are more metal-rich. This gradient reflects the continuous enrichment of the interstellar medium over billions of years of star formation and death. It's like a cosmic timeline etched in the elements, mapping the relentless process of ongoing chemical evolution. Active galactic nuclei, or AGN, which include quasars and blazars, are not just passive inhabitants of galaxies. The powerful jets and winds emanating from these central supermassive black holes can have a profound impact on their host galaxies, sometimes suppressing star formation by heating and expelling gas, and other times triggering it by compressing gas. This intricate feedback loop between the black hole and its galaxy is an active, ongoing process, continually shaping galactic evolution, illustrating that the very heart of a galaxy is a dynamic engine of cosmic change. The process of galactic cannibalism, where larger galaxies engulf smaller satellite galaxies, is a dramatic example of ongoing cosmic formation. The larger galaxy tidally strips stars, gas, and dark matter from the smaller one, ultimately incorporating them into its own structure. This process contributes significantly to the growth of massive galaxies and their halos, changing their morphology and star formation rates. Traces of these ancient feeding frenzies can still be seen today as stellar streams in the halos of many galaxies, including our own Milky Way, a record of ongoing accretion. The formation of the universe's first clusters of galaxies was a monumental step in large-scale structure formation. These primordial clusters, driven by the immense gravity of concentrated dark matter, began to assemble even when the universe was less than 1 billion years old. These early concentrations of galaxies served as gravitational anchors, pulling in more matter and growing into the superclusters we observe today. It was a crucial early phase of ongoing cosmic construction, laying the groundwork for the most massive structures in existence. The study of starburst galaxies provides clear evidence of intense, ongoing star formation. These galaxies are experiencing exceptionally high rates of starbirth, consuming their gas reserves far more rapidly than typical galaxies. Starbursts are often triggered by galactic mergers or close encounters, which compress gas clouds, leading to a flurry of new stellar ignitions. These galaxies are living laboratories for observing extreme, accelerated cosmic formation, demonstrating the powerful influence of galactic interactions on the rate of star creation. Continuous formation of cosmic dust, primarily within the cool atmospheres of aging stars and in the aftermath of supernovae, is essential for new star and planet formation. Dust grains act as crucial catalysts for the formation of molecules in space and provide the initial seeds for planetary accretion. This seemingly tiny component of the cosmos is perpetually being created, destroyed, and recreated, fueling the cycle of heavy element incorporation into new cosmic structures, demonstrating that even minuscule elements are critical for macrocosmic evolution. The formation of molecular hydrogen, the most abundant molecule in the universe, is a continuous process that forms the foundation of all star formation. Individual hydrogen atoms can merge on the surface of cosmic dust grains to form molecular hydrogen. These molecules then cool down, allowing clouds to collapse under gravity and form stars. Without this ongoing molecular hydrogen formation, the universe would lack the raw material in the necessary cooler form to initiate the collapse of gas clouds, profoundly impacting the rate of new star births. The universe's increasing entropy, its tendency towards disorder, is also a form of ongoing change. As the cosmos expands and cools, and as energy becomes more diffuse, the conditions for new star formation will eventually become less favorable in the extremely distant future. While entropy generally promotes disorder, in the short term, over billions of years, gravity acts locally to create structure and order, forming galaxies, stars, and planets. This counterbalance between ongoing formation and the overall march towards entropy dictates the universe's ultimate fate. The formation of the universe's most extreme objects, blazars, represents a peculiar and intense type of cosmic evolution. Blazars are a type of active galactic nucleus, where the powerful jet of matter and energy from the central supermassive black hole is pointed almost directly towards Earth. This unique orientation makes them incredibly bright across the electromagnetic spectrum. Their formation and intense activity illustrate how the geometry and energetic output of central black holes continue to influence the observable universe, acting as cosmic lighthouses of extreme activity. The continued mapping of the cosmic web with new astronomical surveys is revealing ever finer details of its ongoing formation. These surveys allow astronomers to trace the distribution of galaxies and dark matter on scales never before possible. The intricate filaments, knots, and voids are not static. Gravity is constantly pulling matter along the filaments into the denser clusters, and voids are still expanding. These large-scale movements represent the universe's gravitational scaffolding in action, constantly evolving and defining the large-scale distribution of all matter. Galaxy clusters are not isolated islands. They are influenced by cosmic flows, the large-scale movement of matter towards regions of higher density. These flows are driven by the overall gravitational field of the cosmic web, causing entire clusters and filaments to drift slowly through space towards even larger gravitational attractors. This continuous, slow but massive movement of structures indicates that the universe is not just expanding, but its matter is still sorting itself out gravitationally, with structures merging and being drawn into larger basins of attraction. The formation of globular clusters, ancient, densely packed spherical collections of hundreds of thousands of stars, is also part of galactic evolution. While many are very old, some theories suggest that new, distinct globular clusters can still form, particularly in the aftermath of major galactic mergers. These clusters provide insights into the early cosmic conditions under which similar structures might have formed in the nascent universe, demonstrating that this specific type of star grouping can still occur under the right chaotic conditions. Tidal disruption events, where a star strays too close to a supermassive black hole and is ripped apart by its immense gravitational forces, are spectacular examples of ongoing cosmic processes. As the star is spaghettified, some of its material is flung out, while the rest forms a bright accretion disk around the black hole, emitting a luminous flare that can be observed across vast distances. These events contribute to the growth of supermassive black holes and illustrate the extreme, destructive, and yet formative power of gravity. The phenomenon of galactic winds is another powerful driver of ongoing galactic evolution. These are massive outflows of gas, driven by the collective energy of supernovae and active galactic nuclei, that can literally blow gas out of a galaxy. While this often removes fuel for future star formation, the expelled gas can later cool and fall back into the galaxy, or contribute to the intergalactic medium, highlighting a dynamic cycle of creation and dispersal. These winds play a crucial role in regulating the overall star formation rates in galaxies. The ongoing search for primordial black holes, theorized to have formed in the extremely dense conditions of the very early universe, could provide insights into fundamental cosmic formation. Unlike stellar or supermassive black holes, these wouldn't collapse from stars but from direct density fluctuations in the primordial plasma. If detected, they could offer clues about the universe's initial conditions and potentially even account for some or all of the dark matter, representing a type of formation that predates conventional stellar processes. The formation of the first stars and galaxies fundamentally changed the universe by heating and ionizing the neutral hydrogen left over from the Big Bang. This epoch of reionization transformed the opaque, neutral early universe into the transparent, ionized cosmos we see today. It was a massive, ongoing transformation driven by the cumulative light of countless early stars and quasars, marking a profound shift in the universe's state and enabling light to travel freely, allowing us to observe distant galaxies and study their formation. The persistent process of cosmic reionization, initiated by the first stars, continued for nearly 1 billion years. As more and more stars and galaxies formed, Their combined ultraviolet radiation slowly but surely stripped electrons from the neutral hydrogen atoms throughout the intergalactic medium. This process was not instantaneous or uniform, but patchy, with bubbles of ionized gas expanding and merging until the entire universe became mostly transparent. This ongoing phase profoundly influenced galaxy formation by affecting the ability of gas to cool and collapse. The intricate details of galactic archaeology, the study of the oldest stars and their movements within galaxies, provide direct evidence of ongoing galactic assembly. By analyzing the chemistry and trajectories of these ancient stars, astronomers can uncover the remnants of smaller galaxies that were absorbed by larger ones, like the Milky Way. These stellar streams and tidal tails found within galactic halos are fossilized records of ancient mergers, proving that galaxy formation is a continuous process of accretion and integration over billions of years. Even after galaxies have merged to form a larger one, the internal structure continues to evolve. The stars, gas, and dark matter that were disrupted during the collision slowly settle into new configurations. This process, known as relaxation, takes billions of years, driven by gravitational interactions between individual stars and gas clouds. The cosmic architecture is therefore not only formed by dramatic events, but also by the slow, continuous reorganization of its components, a fundamental aspect of ongoing structural evolution. The ongoing formation of stellar streams, long, thin ribbons of stars stretching across galactic halos, is a direct result of ongoing galactic dynamics. These streams are formed when smaller satellite galaxies or globular clusters are gravitationally torn apart by the tidal forces of a larger galaxy. The stars are stretched out into elongated paths, continuing to orbit and slowly disperse over billions of years. These streams are not static, but are themselves evolving structures, eventually blending fully into the larger galactic halo. The continual emergence of hypervelocity stars, ones ejected from a galaxy entirely, represents another fascinating type of cosmic formation. These stars are thought to be flung out at extreme speeds when they have a close encounter with a supermassive black hole at the galactic center, or perhaps during binary stellar interactions in dense clusters. Their escape from the gravitational confines of their host galaxy means new, solo cosmic wanderers are continuously being formed, traversing the vast intergalactic void. The formation of comets, icy remnants from the early solar system, is not an entirely continuous process in the present, but their visible activity represents an ongoing, dynamic transformation. As comets from the distant Oort cloud are occasionally perturbed and fall into the inner solar system, they warm up, sublimate ice, and develop their spectacular tails. This process of sublimation and the consequent release of gas and dust is a visible, ongoing transformation of primordial material, changing the composition of interplanetary space as they decay. The interaction between stellar winds and the interstellar medium is a continuous, dynamic process. All stars shed material through stellar winds, but massive stars have particularly strong ones. These winds create stellar bubbles and bow shocks as they plow through the surrounding gas, shaping the nebula and influencing star formation. This constant churning and mixing of material, driven by stellar outflows, represent a perpetual sculpting of the cosmic landscape, influencing where and when new stars and systems can arise. The discovery of orphan gamma-ray bursts, without an obvious host galaxy, suggests the possibility of star formation in extremely isolated or dark matter-dominated environments. These mysterious events hint that the processes leading to the most powerful explosions in the universe might occur in places previously thought to be devoid of significant stellar activity. This could be a new form of ongoing extreme cosmic evolution, pushing the boundaries of where and how cosmic events can originate, defying conventional expectations. The ongoing search for and characterization of intermediate mass black holes, those between stellar mass and supermassive ones, could offer crucial insights into black hole formation. These elusive objects might form from the collapse of very massive stars, or perhaps through the hierarchical mergers of smaller black holes. Their discovery would bridge a significant gap in our understanding of black hole evolution, providing another piece of the puzzle in how these formidable objects contribute to the ongoing gravitational sculpting of the cosmos. The universe is constantly producing new metals, in the astronomical sense, elements heavier than hydrogen and helium. Every time a star fuses elements in its core, or a supernova explodes, or a neutron-star merger occurs, the cosmic abundance of these heavier elements increases. This continuous chemical enrichment is a fundamental, irreversible form of ongoing cosmic evolution, slowly but surely laying the groundwork for more complex chemistry, planets, and potentially life throughout the cosmos. The continuous cycle of heating and cooling of gas in the intergalactic medium is crucial for ongoing structure formation. Hot gas in galaxy clusters cools and condenses, falling into galaxies and fueling star formation. Conversely, star formation and black hole activity heat gas, expelling it back into the halo or intergalactic medium. This dynamic thermal feedback loop orchestrates the availability of gas for future stellar and galactic growth, a continuous reequilibration that dictates the pace and location of cosmic creation. The formation of the universe's largest galaxy, IC 1101, an elliptical supergiant, serves as a monumental example of ongoing cosmic evolution through mergers. This behemoth is believed to have grown to its enormous size through the continuous accretion and merging of countless smaller galaxies over billions of years. Its sheer scale and the evidence of its composite history stand as a testament to gravity's relentless work in assembling the largest structures in the cosmos, a process that continues even today on grandest scales. Even seemingly empty space is not truly empty. The vacuum of space is teeming with virtual particles that spontaneously pop into and out of existence, a quantum effect that contributes to the mysterious dark energy. While these are fleeting, unobservable directly, their collective effect on the expansion of the universe is a form of ongoing, fundamental change. This constant quantum bubbling hints at an underlying dynamic reality shaping the cosmos, even at its most basic and empty level. Understanding the universe's continuous formation requires increasingly sophisticated astronomical instruments. Telescopes like the James Webb Space Telescope peer back in time to observe the earliest galaxies just as they were forming. Gravitational wave detectors like LIGO are opening a new window to extreme cosmic events previously undetectable. Each new instrument provides sharper images and deeper insights, revealing more layers of ongoing cosmic evolution, pushing the boundaries of our knowledge and revealing new forms of formation. The very act of scientific discovery within cosmology is an ongoing process of unraveling the universe's formation story. Each new observation, each new theoretical model, refines our understanding of how cosmic structures emerge and evolve. This human endeavor mirrors the cosmos itself, a continual process of building upon existing knowledge, expanding our horizons, and forming a more complete picture of the universe around us. Our understanding is always in flux, continually adapting to new evidence. The formation of binary and multiple star systems, where two or more stars orbit each other, is another incredibly common form of ongoing stellar evolution. While single stars like our Sun exist, a significant fraction of stars are born in pairs or larger groups from the same collapsing molecular cloud. Their mutual gravitational interactions not only shape their own orbital dynamics, but can also influence the formation of planets around them, potentially forming complex and diverse planetary systems, adding another layer of intricate cosmic architecture. The ongoing cosmic dawn, the period when the first stars and galaxies fully illuminated the universe, is a key area of study for understanding early formation. Scientists are trying to observe and map the distribution of ionized hydrogen in the early universe, which was produced by these first light sources. This mapping effort is essentially tracing the ongoing reionization process, revealing how the universe transitioned from dark and neutral to bright and transparent, a monumental transformation that allowed light to eventually reach our telescopes. The continuous bombardment of Earth by micrometeorites and cosmic dust represents a subtle form of ongoing planetary accretion. While these additions are minuscule compared to Earth's mass, they nonetheless contribute to the planet's growth over geological timescales and deliver extraterrestrial material to its surface. This process reminds us that even worlds assumed to be finished are still subtly accumulating material from space, participating in the slow, continuous exchange of matter within the solar system. The formation of ring galaxies, rare and distinctive cosmic structures, is another dramatic outcome of ongoing galactic interactions. These galaxies are formed when a smaller galaxy passes directly through the center of a larger disk galaxy, sending a shockwave through its gas and dust. This shockwave compresses material into an expanding ring of intense star formation, creating a visually stunning, transient structure. These are powerful examples of how collisions immediately trigger rapid bursts of new cosmic creation, Formation of jets from active galactic nuclei is a continuous process that can last for millions of years. These powerful collimated beams of plasma, accelerated to near light speed, are driven by the accretion disk around a supermassive black hole. As these jets blast outward, they interact with the surrounding intergalactic medium, creating vast lobes of radio emission and influencing the distribution of gas within galaxy clusters. These ongoing energetic outflows are crucial players in shaping the larger cosmic environment. The universe's persistent background X-ray emission, distinct from the cosmic microwave background, is a result of ongoing high-energy processes. This diffuse glow comes from superheated gas in galaxy clusters, active galactic nuclei, and other energetic phenomena. This pervasive X-ray background serves as a testament to the continuous energy transformations occurring across the cosmos, from the largest structures to the most compact objects, contributing to the overall energy budget of the universe. The hierarchical formation model, which states that larger cosmic structures form from the mergers and accumulation of smaller ones, is a cornerstone of modern cosmology and describes an ongoing process. Galaxies form from proto-galaxies, and galaxy clusters form from the mergers of smaller galaxy groups. This bottom-up assembly means that the universe is continuously building larger and more complex structures from simpler ones, a never-ending gravitational sorting from the smallest to the largest scales. The formation of intracluster light, the faint, diffuse glow observed between galaxies and galaxy clusters, is a fascinating aspect of ongoing cluster evolution. This light comes from stars that have been stripped out of their parent galaxies during gravitational interactions and mergers within the cluster. These wandering stars form a vast, diffuse component, silently adding to the total luminosity of the cluster and serving as a fossil record of countless past gravitational disruptions and incorporations. Even Earth's magnetosphere, our planet's protective magnetic shield, is a product of ongoing internal planetary processes. Generated by the convective motion of molten iron in Earth's outer core, this dynamic field continuously reshapes itself, protecting us from harmful solar radiation and cosmic rays. This internal dynamism ensures the habitability of our planet, showcasing that the ongoing formation relevant for life is also occurring deep within planetary bodies themselves, a hidden, constant process. The continuous activity of the Sun itself, with its solar flares and coronal mass ejections, represents ongoing local cosmic dynamism. These powerful eruptions of energy and plasma from the Sun's surface constantly reshape the interplanetary environment, creating space weather that can impact Earth's technology. This fundamental stellar activity, driven by magnetic field lines, is a constant reminder that our own star is a dynamic, active participant in the ongoing subtle formation and transformation of our immediate cosmic neighborhood. Formation of rogue planets, those unbound by a star's gravity and wandering through interstellar space, adds another dimension to planetary formation. These worlds may have been ejected from their birth systems during chaotic early stages of formation, or perhaps formed independently in dense molecular clouds without a parent star. Their existence suggests that the universe's ongoing planetary formation yields not just neatly ordered systems, but also opens up possibilities for countless solo worlds traversing the cosmic void, a testament to the diverse outcomes of gravitational dynamics. The study of exoplanetary atmospheres is revealing surprising details about the ongoing chemical evolution on other worlds. For instance, observations indicate processes like cloud formation, atmospheric escape, and even weather patterns on distant worlds. The presence of specific molecules can indicate geochemical cycles or even potential biological activity, hinting at the continuous reshaping of these alien environments. These atmospheric dynamics serve as a reminder that the formation and evolution of a planet don't cease after its initial accretion, but continue throughout its entire lifetime, a never-ending interplay of forces. Even within star clusters, the ongoing gravitational interactions between stars are constantly reshaping their structure. Over millions of years, closer encounters and gravitational slingshots can eject stars from the cluster, or cause others to merge, forming runaway stars or even new, more massive stars. This internal dynamism means that even tightly bound groups of stars are far from static, continuously evolving their stellar compositions and distributions. The formation of the chemical precursors of life, complex organic molecules, in molecular clouds and protoplanetary disks is an ongoing process throughout the galaxy. These molecules are observed in vast quantities, floating freely in interstellar space, or incorporated into comets and asteroids. Their ubiquitous presence suggests that the fundamental building blocks for life are continuously being synthesized in the cosmos, long before they ever reach a suitable planet, a critical stage in the universe's chemical evolution towards biological complexity. The phenomenon of cosmic filaments acting as channels for gas flow is an active area of research demonstrating ongoing cosmic formation. Observations suggest that cool, pristine gas from the intergalactic medium is continuously flowing along these dark matter filaments towards galaxies, providing them with a steady supply of fuel for star formation. This accretion of fresh, often metal-poor gas is a vital continuous input, preventing galaxies from running out of material for new stellar births. The universe's eventual fate is deeply tied to its ongoing formation and expansion. If dark energy continues to dominate, the universe might face a big freeze, where structures become increasingly isolated and stars eventually burn out, leading to a cold, dark, and empty cosmos. Alternatively, a big rip could occur, where dark energy tears apart even atoms. These future scenarios are extreme projections of current ongoing processes, emphasizing that the universe's evolution is a continuous journey towards a yet unknown cosmic destiny. The ongoing search for alien life, particularly microbial life in our solar system or on exoplanets, is a frontier of discovery that ties directly into the universe's ongoing formation of complex systems. If life is found elsewhere, it would imply that the conditions and processes conducive to its emergence are more widespread than currently understood, making the ongoing formation of habitable environments and complex chemistry even more profound. Life itself becomes another layer of ongoing cosmic evolution. The continuous improvement of computer simulations, known as n-body simulations and hydrodynamic simulations, allows cosmologists to model the universe's ongoing formation with increasing accuracy. These simulations input fundamental physics and initial conditions, then track the gravitational interactions and fluid dynamics of billions of particles over cosmic timescales. They are crucial tools for testing theories about dark matter, dark energy, and the formation of cosmic structures, constantly refining our understanding of how the universe is built. Continuous shedding of gas from galaxies into the intergalactic medium during violent events like quasar outbursts or galactic winds leads to the ongoing formation of the circumgalactic medium. This vast, diffuse halo of hot gas surrounds galaxies, acting as a reservoir of material that can eventually fall back onto the galaxy. This medium is constantly being enriched by outflows from the galaxy and shaped by its gravitational potential, demonstrating a dynamic interplay of matter beyond the galactic disk itself. The formation of the universe's cosmic background light, the sum of all light emitted by stars and galaxies throughout cosmic history, is an ongoing accumulation. While the cosmic microwave background is from the early Big Bang, the cosmic optical and infrared backgrounds are continuously being augmented by new stellar and galactic emissions. This faint, pervasive glow is a fossil record of all the light-producing events that have ever happened in the universe, a continuous, growing testament to all the stars that have ever formed. The continued detection of fast radio bursts (FRBs), extremely powerful millisecond-duration radio emissions from distant galaxies, presents another ongoing mystery of cosmic formation. Their origins are still unknown but theorized to involve extreme objects like neutron stars or magnetars. Each new FRB detection provides more data to understand these enigmatic phenomena, revealing new types of powerful, transient events continually occurring in the universe, challenging and expanding our understanding of high-energy astrophysics. The ongoing processes shaping planetary surfaces, even long after their initial formation, are crucial for their evolution. On Venus, active volcanism reshapes its surface. On Mars, dust storms and polar ice cap changes constantly erode and deposit material, and on Jovian moons like Io, intense volcanism is ongoing. These dynamic processes demonstrate that worlds are not static, but are continuously forming and reforming their landscapes through geological and atmospheric forces, exhibiting a ceaseless planetary metamorphosis. The relentless decay of radioactive elements within planets provides an ongoing internal heat source that powers geological activity. This slow, continuous release of energy drives processes like plate tectonics on Earth, volcanism on Venus, and internal dynamics on other rocky bodies. This internal furnace, born from elements forged in ancient stars, ensures that planetary formation and evolution are not just external processes, but also result from the continuous transformation and release of energy from within. The formation of cosmic rays, high-energy particles originating from outside our solar system, offers another fascinating glimpse into the universe's dynamic processes. These particles, mostly protons and atomic nuclei, are accelerated to nearly the speed of light by powerful cosmic events like supernovae, active galactic nuclei, and colliding galaxies. They traverse vast distances, carrying information about the extreme environments where they are formed. Their continuous bombardment of our planet and atmosphere is a subtle but constant reminder of the intense, ongoing energy transformations occurring throughout the cosmos. Even beyond stellar mass and supermassive black holes, theorists explore the possibility of intermediate black holes, which bridge the gap in mass between the two known types. These objects could form through the mergers of many stellar black holes in dense star clusters, or from the direct collapse of very massive stars in the early universe. Their potential existence and formation mechanisms would offer crucial insights into the complete spectrum of ongoing gravitational collapse across all mass scales. The ongoing formation of very large structures, namely superclusters of galaxies, demonstrates the universe's continuous gravitational pull towards immense concentrations of matter. Superclusters are collections of galaxy clusters, sprawling across hundreds of millions of light-years. Though they are not gravitationally bound as a whole, they are still actively drawing in more galaxies and clusters, slowly but relentlessly building the largest, loosely bound structures in the cosmos. Acting as gravitational basins on the grandest conceivable scale, the universe's ongoing evolution is not a smooth, uniform process. It is punctuated by periods of intense activity, like bursts of star formation after a galaxy merger, contrasted with periods of relative quiescence. This episodic nature of creation and change ensures a rich diversity of cosmic structures at various stages of their lifespan, from nascent protostars to quiescent elliptical galaxies. This ebb and flow illustrates the complex interplay of forces that define the universe's dynamic history. The continuing formation of our intellectual understanding of the cosmos is itself a testament to human curiosity. From ancient stargazers to modern cosmologists, each generation builds upon the knowledge of the last, forming new theories and discovering new phenomena. This collective journey of discovery is an ongoing, evolving process, mirroring the very universe it seeks to comprehend, as our models and observations become ever more refined and insightful. The universe's ongoing formation challenges our preconceived notions of stasis and permanence. It is a vibrant, continuously transforming entity where creation and destruction are intimately linked. Every observation, from the farthest galaxy to the nearest star, underscores this fundamental truth. Our place within this actively forming cosmos is humbling, yet inspiring, recognizing that we are but a brief, conscious part of an unimaginably grand and endless cosmic narrative. This journey through the cosmos reveals a universe that is far from static. It is a canvas of perpetual transformation, from the subtle shifts in planetary atmospheres to the collision of colossal galaxies. The forces of gravity, energy, and matter are actively shaping reality at every scale. The universe is truly still forming right now, and the processes we've discussed are not relics of the past, but active, ongoing phenomena that continue to define the cosmic landscape, leading us deeper into the grand mystery of existence. The sheer scale of cosmic formation, stretching across billions of years and unimaginable distances, reminds us of the profound patience of the universe. Processes that seem instantaneous to us, like a supernova, are often part of much longer cycles of stellar evolution that span millions of years. And processes like galaxy mergers unfold over billions of years. This vast temporal scope underscores that cosmic change is a relentless, continuous force, far beyond human perception of time. Our ongoing quest to discover more exoplanets is a direct search for more examples of ongoing planetary formation. Every new exoplanet confirms the universality of these processes and provides clues about the myriad ways worlds can form and evolve. From hot Jupiters to super-Earths to icy ocean worlds, each discovery expands our catalog of cosmic creations, highlighting the truly astonishing diversity of planetary architectures that are continuously being constructed throughout the cosmos. The universe's ongoing formation is intricately linked with its expansion. Dark energy continuously pushes galaxies apart, yet within gravitationally bound groups, gravity still pulls them together. This dynamic tension shapes the overall structure of the cosmos, determining which structures will continue to grow and which will eventually become isolated. It's a delicate balance of cosmic forces that dictates the ultimate fate of structures and the universe at large. The profound realization that the cosmos is an active, living entity, constantly in flux, deepens our appreciation for its majesty. We are not just observers of a finished product, but witnesses to a grand, ongoing symphony of creation. Every moment, new stars ignite, galaxies collide, and the fabric of space-time itself continues its remarkable transformation. This perspective transforms the night sky from a static tapestry into an endlessly dynamic stage, where the greatest drama of cosmic formation truly never ends. And so, the journey into the cosmos, into the heart of its continuous formation, is also a journey into ourselves. We are products of this ceaseless cosmic evolution, made of stardust, and our minds are capable of unraveling its enduring mysteries. The universe is not just forming out there, it is continuously forming our understanding, inspiring our awe, and challenging us to look deeper, to question more, and to always remember that the greatest show of all is truly a work in progress, forever unfolding.